track width capabilities they do offer. So this is the minimum track that we can use in our design. The track width technologies that we can find on the market, the standards, the poor standard, the very cheap standards, you can see here. So this is 10 mils or 0.25 millimeters. So we mentioned about the mixing of mils, of inch, imperial and metric units, and here it is. So we have either a 0.25 or 10 mils. This is the cheap class, the cheapest manufacturer. So all the manufacturers outside in the world are offering this capability. So to make the TW of 10 nanometers of 10 mils or 250 micrometers in metric units. Here we have also in this class the parameter of OTW and the parameter of ITW.
Next time on like Richie or something, we broke up.
Please switch off a microphone. Hello, hello. Please switch off a microphone if you don't want to ask a question.
Text anyone else?
Yeah?
I didn't text anyone from our class.
Who did you text?
Is it a question? Because
That's it, right?
Okay, let's consider it is not. Actually, we have we have the in the table two parameters, OTW and ITW. OTW and ITW are the, of course, outer track width and inner track width. The outer track width is only above the top layer and bottom layer. That's the accuracy of top layer and bottom layer. Mind that with in case of layer stack layer, they are those overlays. So top overlay and bottom overlay. Those are not they do not stick to this regulation. So the accuracy class is only about the copper, not about any descriptions on the PCB. So the quality of the overlay and the mask layers is always weaker or worse than the quality of the copper. I think that's quite natural. Anyway, in some situations the ITW is different than the OTW, but only for some manufacturers. For this actual manufacturer, so this is Eurocircuits, the ITW and OTW is the same. So going back to the values we can expect, 0.25 millimeters is really the cheapest option and available always. The always low class manufacturers are offering what is here class 4, so 8 mils. 8 mils is today a standard for double-sided boards, and 10 mils is something that makes it in a garage. But for companies delivering PCBs, 8 mils is really a minimum today. Then we go to higher classes, so like 7 mils, 6 mils class. This is not so obvious. So actually 7 mils is rare. Usually we are having manufacturers that are offering 10 mils, 8 mils, then 6 mils class. And then the next class is usually the 4 mils class. Although 4 mils, which is 0.1 millimeter, so mind how thin the tracks are, 0.1 millimeter, this is the high class already, actually. 6 mils is decent, 4 mils is very good. Anything better than 4 mils, which is actually for this manufacturer class 10 of PCBs, we have less than 3.5 mils. That's usually extremely expensive. Not to mention that the price rises from class to class. Class 3 and class 4 usually are priced same way, because class 3 is really a garage technology. You can do it at home. I will show you how in a moment. So class 3 boards here, class 3 according to this producer, so 10 mils boards. But getting to 4 mils or even better than 4 mils is very difficult. Anyway, that's the technology limit you can find when you design a PCB board. This is really the first and utmost parameter that is defining usually the rest for us, because we start with TW parameter and we take all the other parameters from the class for granted. So what are the other parameters then? So let's take a look at the other parameters here. So let's consider that we have chosen that we are in this class, for example, 0.15 millimeters. So what are the other parameters? The other parameters that we have on the boards are the TT, so the distance between boards, the track separation. Then the track to path, so this is track to track, that's why TT. And then we have TP, which is that track to path. Then we have PP parameter, which is the path to path separation. And then we have the path size from the obvious parameters ones, and then we have the parameters of OAR, which is the parameter of the annular ring diameter, and the parameter of the that's for the outer layer, and then the parameter for the inner layer, the IPI, inner pie insulation, less important. In case of the most obvious one, because let's start for something from the top. So the TT, TP, and PP, those parameters are usually, like you can see here, they are usually same like TW. That's the case for this manufacturer, because OTW, OTT, OTP, OPP, that's not the this is not the arithmetic operation. It's just that all the parameters are in one line because they are actually the same. So they all have 3, 4 mils and so on. So the distances between tracks are the same like track width. That's the reason why the TW parameter is actually by far the most important, because it does really defines many parameters, many limits we have on the design limits we have in our development process, design process, PCB design process. So the TW, TT, TP, and PP, so all those parameters are actually the same. For majority of manufacturers, at least in the situations I know. That's for the inner layer, and for the outer layer, and same is for the inner layer. So the ITT, ITP, and IPP that you can expect are also same like the ITW. So the inner layer width. Here for this manufacturers, the inner and outer values of TW, TT, TP, and PP are the same. But it's not a rule. So they are manufacturers, I know that they offer difference. So the inner layer are better usually than the outer. So the capabilities are slightly better. But again, it depends on the manufacturer. And then we have the completely another parameter, but again very important. This time, considering all the holes we have in a PCB, so the vias and the paths, especially the vias, so the paths connecting two tracks are of very much importance because of their high number of them on the board, and because of their their size, because they occupy more than a track. Remember that the via, normally we have there is a pad on the top layer, a track on the top layer, a via, and the track on the bottom layer. And the via, the diameter of the via is always larger than the thickness of the track. This results from the fact that the via size or the minimum hole size, because it's actually via is a hole, it's always PhD plus 2 times OAR. And take a look, OAR, so annular ring, output annular ring, is better than theoretically than the class of the track, although not than the width of the track, because in class 8 and 7-8 it's not, because it's these are really sophisticated classes. But in the base classes, base options, AR is lower than TW. But still, for the complete diameter of the via, we have to use 2 of those. So for example, for the class 6, let's say, we have track width of 6. But then the OAR, 2 OARs is 10 actually, because it's 5. So it's at least 10. Plus we have to add the PhD, which is the hole diameter, production hole diameter. And the production hole diameter we have here. So this is, it's different because it's not a copper. It's actually a hole, a physical hole. And the limits that are resulting not from the etching process, because that's where the truck width depends on, but the annual ring size depends on, but on the capabilities in the factory, on the tools the factory are using. So some today's either drills, sometimes lasers are used for this purpose, but lasers are more expensive and they are used very much more expensive. Laser drills, let's say, or burned holes are way more expensive. So today still people are using drills. So in the companies, the drills are used, but take a look, the drills have the sizes of 0.6 millimeters, 0.45, 0.35. Of course, this is the finish hole, which means that the drill is slightly larger used, but still, this is very tiny. So imagine a drill with 0.5 millimeter diameter or less. How accurate the drill must be and how strong material must be used for this drill. Of course, how expensive the drill would be. That's another problem. So for if we have class 6, and let's consider for drilling a class C, then we have altogether 5 mils. So 0. Let's say metric, 0.125 millimeters, so 0.25, 2 ARs plus 0.35. This is for PhD, which means that here the minimum is 0.6 millimeter. And in class 6, the track width is just 0.15. So that's why the vias are very important, because they really take much more space in our PCB design. You will see by yourself when you try to work with BGA cases, for example, or LGA cases, how much space and how problematic the vias are. And how problematic these limits are. So the OER and PhD, they do really constitute quite a lot of problem. From less important parameters, we've got the inner annual ring. So the size of the ring in the internal layer. Less important, but still sometimes maybe necessary to consider. So the IPI as well. So the inner. So this parameter, so the ring, the insulation part on the internal layers, because here the insulation, we don't care very much about this insulation, because we could have this OPI parameter defined here, because it's actually the same. Yet on the outer layer, it's really no meaning, or the meaning is very small, the accuracy of the OPI, but the IPI ring is important. Its size sometimes is important, and not frankly that's not of the major importance today, at least at first shot. The IAR and IPI, yeah, you can omit it. You can simply omit them for your applications. Actually, another important thing that you have to analyze and you have to choose before you go further with a design, before you even start the design, because these classes, the proper class and all the dimensions that they are defined within a class, you really must know before you start a PCB design. This is really a must. So you can't start. I would even say you mustn't start before you settle the class, settle all the dimensions, before you know all the dimensions, which are the limits for the technology that you will use. So if IPI and IAR parameters are not important, then this parameter, so this table is important. What this table is telling us about, this table is combining the the limits about the track width with the thickness of copper that we are using. The copper thickness that we have a choice normally ranges from 12 to 105 micrometers. The values are very strange because again, these are metric, and originally the copper thickness was defined with imperial unit, with ounces. So here the values are round. For metric are not really round. Yet that's the way we do it. We do it today in the electronic industry. The major and the base copper for the outer layers that is used, the first choice and the base price is 35 microns. It's 35 microns. This 35 microns. In case of 35 microns, the minimum OTW class is 5, but the minimum OTT, OTP, and OPP limit is 7, which does mean that if you want a class 5 board, then you can have for this manufacturer, then you can use 35 micrometer copper. But if you want class 6, for example, of course, you can order class 6, but the manufacturer then will deliver you 18 microns copper PCB. 18 microns, what's the penalty? Because it doesn't have to be more expensive, actually. But what's the penalty of using thinner copper? The penalty is the resistance of the tracks, which means that they are thinner. So to keep the cross section, we'll talk about the resistance of the tracks in a moment, but to keep the cross section, the area same, we must extend their width because they are thinner, so they have to be, they're half the height, so they must be twice the width. So we have better technology like 5 mils, good, actually very nice. But the tracks we must make wider. The tracks, of course, that are to withstand high currents. For the inner layer, the technology is slightly milder. So even if you can use for outer layer 7, if you are forced to keep the track distance of 7 mils, or the distance between pads or between track and pads to keep 7 at this 35 microns, still at the inner layers you can be more fine, more accurate with 5 mils or 0.125 millimeters. These are actually the most important parameters. That you must know before a design process begins. So TW is really the most the major parameter, but also the copper layer cannot be neglected. So the standard is 35 microns. But as you can see, there is a close connection between the copper thickness and the allowable or possible track width. Okay, now we talked about the via. And now a few remarks about the vias, about the tracks, about their electrical properties, actually, of those elements. And so in case of the via, we mentioned about their importance. So we have a trace, and the trace gets to the on some layer, because it can be between the layers, between top and bottom, but it can be as well between the internal layers. But the construction is actually the same. So we have, from technological point of view, there is drilled a hole, and then there is chemically there is made a metallization, which is a connection between the layers. So we have actually a copper connection between the layers. This seems very strong, and this seems very high quality. But unfortunately it's not always so, and especially for cheaper manufacturers, the vias tend to break over time. Same problem is if we order if we don't keep these parameters, so OER and PhD. So if we don't keep the parameters, so it's always better from my experience, it's always better to use in your designs values of OER and PhD a tad higher than the manufacturer declares. So if we choose, if we pay for class 3 with 0.35 and class 6 for 6 mils, so for 5 mils OER, use 6 mils here at least, and 0.40 at least as the whole diameter. Don't try actually to push the limit. Believe me, it's very expensive when the cracks appear. The problem is, from my experience, years-long experience, that sometimes the cracks on the vias appear months or years after after manufacturing. The broken via means replacement of the whole PCB. It's unfixable, so it's very difficult to fix the broken via, because tracing where the via is broken is extremely difficult. You've got usually hundreds of vias on the PCB. So small warning. Try to make the OER and PhD slightly higher in your design than it's allowed, in order to avoid the cracks in the future. What other parameters do we have to cope with besides the geometrical parameters? These are inductance and capacitance. The formula for calculation of inductance of the via and the capacitance of the via you have on the screen. These are important parameters. Important for high frequency. Why? Because take a look, there is a small example, small calculation, 0.4 millimeter via with a small one with a standard FR4 board, so 1.6 millimeter thick PCB. The inductance is 1.2 nanohenry. Okay, somebody may ask, 1 nanohenry? That's nothing. Okay. But let's make a small calculation. Module of impedance, small one, omega L, which is of course 2PF L. And let's consider 2.4 gigahertz, which is actually something used very often today, because we have Wi-Fi, we have Bluetooth, we have OpenThread, we have Zigbee. So Internet of Things is around us, and 2.4 gigahertz is a very common frequency. So take a look. 2 pi times 2.4 times 2.4 times 1.8 1.2 sorry, nanohenry. Of course, nano and giga we can cancel, because it's 10 to 9 and 10 to minus 9. All this gives us 3.6 time let me use a calculator for this. Let me use a calculator to give you the exact value. 2 times 3.1415 times 2.4 times 1.2, and the value is 18 ohm. 18 ohm. It's the impedance of it's the resistance for 2.4 gigahertz of that the 2.4 gigahertz signal will meet when passing through via. Of course, DC impedance, so DC resistance of the VI is very, very low. We talk here about the micro ohms even, so it's negligible. That's why there is no formula here. But the inductance of the VIA matters. The inductance of the VIA matters. Of course, we should tend to reduce for the reduction of the inductance. How to reduce the inductance? We have to reduce the height. So the thinner the PCB, the inductance will be lower, because then the VIA actually geometrically will be smaller, and the inductance will be lower. The D might be higher as well, then the logarithm here will be lower, but the height has higher influence. Also non-negligible is capacitance, but the capacitance influence is not that high because we've got picofarads. Pico is lower than nano by 3 orders of magnitude. Therefore, the capacitance of the via is, from practical point of view, not that important. But the inductance, as you can see, definitely matters. Sometimes we have characteristic impedance calculated. That's especially critical when we try to make a 50 ohm lines or 25 controlled impedance lines. That's for higher frequency. When you make a PCB design for higher frequency, that's something we play with. But frankly, for controlled impedance traces, we usually don't use vias at all. That's usually the case. Because of this, we usually don't use vias at all for controlled impedance paths, and that's why about the characteristic impedance and about the propagation time, because this is the formula for propagation time. Usually we don't bother because usually we don't use it for high frequency. The vias are used for low frequencies, no problem, but for high frequency paths, try to avoid them as much as possible. You can't avoid, if you can avoid the vias, of course you can't avoid the trace itself. So what about the parameters of the copper trace? The first parameter that we have here that we have to analyze is the trace resistance. As you shall be able to shall know from the physics, the resistivity of the resistance of the track depends on its volume and on its resistivity. We are using copper. Which means that the resistivity is 1.724 microns per each centimeter. For the height of 3.6 microns for 1 ounce of copper, so for 35 microns, so it's 35 microns. It's one ounce of copper, so the standard size. So for the standard 35 micrometer copper track, we have this impedance. Of course, this is just the formula, and you can try to calculate with it. Yet, from practical point of view, I think that way more important are those two charts. What they to tell us about? Actually, they tell us about how much the temperature of a track will rise at a certain cross section of the copper track, and at a certain current flowing through the track. So this is very important. So of course, this formula is very good for calculating some exercises, for making some exercises, physical one. But from electronic or engineering point of view, those charts you must have always somewhere during the development process, or you must memorize them in some way, because they have to be viewed once in a while when you are preparing the proper track width, when you are choosing a track width for certain signals. So how do we read this? Because we have top and bottom chart, and on the top one we have a current against the cross-section, track cross-section, and the resulting temperature rise at the desired track temperature rise. While on the bottom we've got the track width against the cross-section at a certain thickness of copper. And we've got so for the standard copper for 35 microns, if we want to have the standard 8 mils, because the 10 mils track is very often used in practice. So we are actually designing today for signals. We are using mainly 10 mils plus minus 2 mils tracks. So 10 mils, 6 mils, or 12 mils for low density designs. Medium density designs, for medium density PCBs, 8 or 10 mils, so 0.2 or 0.25 millimeter tracks we are using. So let's consider this 10 mils track. And this 10 mils track, we are here. So then we can read what current can flow through such a track in order to keep the temperature of the track within limit. What happens if we go beyond this limit? So, for example, what happens if we go here, somewhere here, and the track goes beyond 100 degrees? Our board will melt. We talked last time about the parameter of glass phase of the PCB. We mustn't exceed this TG parameter, and the TG, remember, it's 160. More or less for FR3, FR4 board, sometimes slightly less, even sometimes 140. So it depends on the manufacturer of the PCB board. And remember, this is just about the track, the temperature rise of the track. So even if we are at the 100 degrees, even if we keep our design here, it does mean that the track will be 100 degrees hotter than the PCB. But the PCB doesn't need to be 20 degrees. If the track would be 100 degrees hotter than the PCB, then the PCB would probably will be hotter than 20 degrees as well, which is the very straight way to melt to cross the TG point and to damage the PCB. The effect will be that the FR4 board will burn simply. So we'll start not with flames, of course, but will be black and will start to smell. So the standard electronic smell of the burnt PCB will appear. So actually, getting to this point is usually very, very dangerous. And in my opinion, you shouldn't cross 20 degrees cross point. That's fairly safe. This 20 degrees cross point, because of course it will heat up the PCB and it will heat up the surrounding. But still, from 20 degrees rise, we still have quite a long way to TG. To the TG value. And what about the 20 degrees? At 20 degrees, the 10 mils track can convey about 1 amp. So about 1 amp we can use, of course, at 20 degrees rise of the track. The question to you now, simple one, why at 1 amp the temperature of the track will rise? What stands behind this temperature rise? Simple question. Who knows the answer? What stands behind? Which parameter of the track is responsible for this temperature rise at certain current? Anybody? You can write in comments if you don't want to use a microphone. Of course, resistance. Of course, resistance. I didn't see the comment first. 1 nanohenry is sometimes used in DC converters. Yes, it is. No, not really. 1 microhenry. About DC converters are using. So the answer to Jakub first, because I haven't noticed the question. The 1 nanohenry is not used in DC converters because it's too low for megahertz range. Nanohertz starts to matter at gigahertz. So we are using for high frequency only nanohenry inductors. For DC converters, we talk about microhenries and even millihenries, sometimes for low frequency DC converters. In case of the second note from Jakub, yes, it is resistance, of course. So that's why simple question, simple answer. The track resistance is responsible for the temperature rise. But what does it mean? The track resistance. It of course means, because I said that 20 degrees is for me the maximum temperature rise, but the reason for this is not the temperature, because the temperature is of course one point of the problem, but of course the temperature results from the power. So the power loss results from the temperature. But if we have a power loss here, naturally there will be a certain voltage drop. So if we can calculate it, but I suggest you do it. You do it at home. You try to use those formulas to make the calculations and those charts. Because the voltage drop, if there is the high temperature rise of the track, there will be also a significant voltage drop on the track. The voltage drop calculated within, so it depends, of course, on the track wave, but it will be within millivolts and not within single millivolts, but it may be within hundreds of millivolts even at the higher temperature rises. So that's why actually we should, 20 degrees is really the 20 degrees rise is really the critical value, in my opinion, but it means that you should be lower. So you should actually have a work point somewhere here, you shouldn't get to this point at all. So you should have lower current, which also means that it's always better to use as wide track as possible, at least for low frequency boards, because for high frequency this results in higher capacitance and inductance, which we don't really want. But that's for high frequencies, that's another issue. But for majority of PCBs, it's always better to use wider tracks, like here with 0.7 75 millimeters, which is 24 mils, because for example with this track you still stay within 10 degrees even with more than 1 amp flowing. So and of course at the other side, be warned about these very tiny tracks. So 4 mils is somewhere here. So 4 mils tracks is somewhere here, and 4 mils, with 4 mils you can there can flow through this 4 mils track only small currents like 0.1 amp or even lower, because this is 0.2 line, because this is logarithmic scale, kind of a logarithmic, let's say. Nah, that's not logarithmic. It's strange scale. Anyway, that's about 0.1, 0.2 amp can flow only through 4 mils track. So be careful here. Try use as wide tracks as available. Of course, here we can see as well from this chart, then if you really need high current flowing through a track, then you should consider the copper with higher height. So instead of 35 microns copper, you should get to 70 or 105 microns. At 105 microns, so at very thick copper, then using the 24 mils. It's somewhere here. It's a 24 mils, so 0.75 millimeters. But instead of a 1 amp, we can convey almost 4 amps, and with still temperature rising less than 10 degrees. That's the advantage. By the way, going back, for 4 mils track, we usually have 17 microns copper, so it's even worse in case of 4 mils track, because with 4 mils track we are actually here, so the current flowing, the maximum current flowing, not heating up the track more than 10 degrees, is not even 0.1 amp, but it would be in tens of milliamps region. So be very careful about very thin tracks. 8 mils is really good here. Less you always have to think. And The next, yeah. Would it be possible to break melt signal tracks that are carrying high frequency signals? So a question. Yes, it would be possible. Yes, it would be possible. Actually, in case of high frequency signals, there is always a trade-off between the parameters, so the characteristic impedance, because that's what we are caring about, and the size of the high frequency track. Yet normally that's not such a problem. So that's the problem if you design if you are designing a high frequency transmitter, because for high frequency transmitter the high frequency transmitters can require a few watts of power, which has to be delivered from the transmitter to the antenna, and then we have to play with high frequency tracks, and we have to design it properly so it doesn't burn. Normally that's not an issue, because when we are designing the standard transmitters and standard receivers, these are milliwatt receivers and milliwatt transmitters, because normally for the ISM bands, for the industrial, scientific, and medical bands, we are not allowed simply to use watt transmitters, such very high power transmitters. Besides the power planes or delivering of DC power, then the DC power is so the RF is low power. Then the DC power is higher in such transmitters, because the transmitters have, of course, some certain efficiency, but the DC is just a DC, so then it's not a problem. It's not a high frequency path. So again, that's a problem, true, but only in a very special cases. So only when you will be designing a high frequency transmitter, a dedicated one with watt or tens of watts of power, only then you will have to think about it. In all the other cases of standard Internet of Things applications or computer applications, not at all. So that's not a problem. Okay, so it's time. So we have next parameters like the capacitance and inductance, but it will take us a while, and it's already a break. So let's have a 15 minutes break, and after the break, we'll get back to this subject. We are back. So after the resistance, next thing is a capacitance. Capacitance, which is defined, of course, it depends on the area of the plane or of the path or of the track, and inversely, it's proportional as well to the permeability of the material, which is actually about 4, or slightly more for the FR4 PCB, but it's inversely proportional to the thickness of the PCB board. For the standard FR4 thick FR4, not standard, the calculations are for 0.8 millimeter. For standard, it will be half of this, so each square centimeter is 0.5 picofarad. For 1.6 millimeter FR4, it would be 0.25 picofarad. That's not a high value, and actually the plane capacitance it's especially it's here the name I use for purpose. It's not track capacitance, but plane capacitance, because what we are interested in actually is to use this capacitance not actually as a parasite. The parasite is for high frequency, at very high frequencies, then the capacitance starts to play a role, but it's about gigahertz and not single but tens of gigahertz rather. But the plane capacitance, the capacitance of the PCB or the capacitance between the layers, start to play, and it is used for filtering out the noises. So the capacitance, as it will be shown later in a few slides, this capacitance actually we are using to decouple signals between themselves, and then those picofarads, they seem not too much, but if we use a high area of the plane, so not square centimeter, but if we use use a plane all over our PCB board, then this capacitance will go from picofarads to tens of picofarads, maybe hundreds, depends on the size of the board, and then the strength of the decoupling will be large. So the capacitance of the PCB is used for a good purpose. Actually, it's not always harmful. In case of trace inductance, it's also sometimes used for a good purpose. Like instead of lumped elements, we are using tracks to form antennas, for example, for high frequency IoT circuits and IoT transmitters. But in many cases, the inductance poses a lot of problems, poses a lot of troubles. Anyway, it has to be understood, and it has to be taken into account, even for not so very high frequencies. Why? Take a look. Simple via means 1.2 roughly nanohenries of inductance, which means it for 2.4 gigahertz, 18 ohms. About impedance, but what about the impedance of a strip or the impedance of a wire? Well, we have 1 centimeter of a thin wire, output diameter 0.5 millimeter, 7 nanohenries for 1 centimeter wire, only 1 centimeter, mind that. And same about the track, so 38 microns track, so the standard track width, with 10 mils width, standard height, standard width, 1 centimeter of such track would have 10 nanohenries of the inductance, which means that at 2.4 gigahertz, such a track would yield about 180 ohms of impedance. 180 ohms, mind that. Horrible impedance. Of course, we have to we are avoiding it normally, reducing the length of the track, reducing the width of the track as well. Sometimes the height of the track we reduce as well. So there is certain trade-off here about between the power and the electrical capability. Still, that's definitely not negligible value. And for high frequencies, be very careful designing your PCB boards. And then next part of the PCB, the grounding, something that is, at least by the beginners, it's avoided, it's omitted, it's neglected. So connecting our devices, the pads, or the capacitors, resistors, and so on, whatever we have on our PCB, to a ground. The grounding of a PCB is really fundamental to the operation of many circuits. And as it is written down in the second point, a good or bad grounding technique can make or break your design, which means that it's either something will work or your project will fail. So the grounding, the fundamental here is a strong word, but that is how it is in reality. So the grounding is really important. So there are several grounding techniques, and those grounding techniques must be used during the routing on the PCB. So the major grounding techniques that we are using are single source point, multi-point source, and star. So single point, multi-point, and star. The difference is especially important between the multi-point and the other two techniques, because the star and the single point is actually very much similar. It's only about where the difference only is where the middle connection is placed and how far is from the middle point. So from the ground point to the ground connection to each of the element, each of the components on our PCB track. Here in the start, the distance is fairly the same, so we have fairly similar distances, while in a single source point they are components which are much closer than the other ones. And the worst always is the multi-point. The worst always is the multi-point. Actually, we shouldn't be using this technique at all in our design, or we should reduce the use of this technique only to the points which are not very much ground quality sensitive, because it happens sometimes for simple microcontroller designs. For example, we can try to use the multi-point, so we can connect the ground between each of the component on a PCB, between the ICs or some other semiconductor or passive component. This technique is the very worst one. Why? Because take a look. It works this way. Each line actually has certain impedance. Impedance for power and impedance, so DC in the DC scale, but even worse, the impedance for the high frequency circuitry, as we mentioned, a simple via at 2.4 gigahertz, 18 ohm. And then with this technique, on the ground plane there is a current flowing. So if from this user, let's say there is this current flowing, then here the current is higher, because we have current from here and from here as well. Summed up, here we have already tripled the current, and then we have here the current is getting even higher, and here the current is getting even higher. Of course, that's the way this technique is working. That's not happening here, by the way. That's not happening here, because here on each line the same current is flowing. Same situation we have naturally here with the star technique. Okay, and with the multi-point, it does mean that this impedance, because the highest current we have here, this impedance this impedance with this high current will induce a very high voltage drop. And this voltage drop may exist in the DC scale, but of course for the power, but for high frequency signals it's especially painful because it will cause also some drops at the high frequencies. The drops here, what values can we expect here within such a circuit in real life? I would say easily hundreds of millivolts. Not 100, but hundreds of millivolts. Such voltage drops may exist. I even experienced when I was young, when I was stupid. Not that I'm very clever now, but when I was younger, I'd say this way. I used to construct such circuits, and the voltage dropped were half a volt, 0.7 in some of my designs. So that's not something we want. That's not something we like. Sometimes the circuit, the problem is that the circuit with constructed against the multi-point technique, against the multi-point connection scheme, the circuit works actually, because sometimes this 100 millivolts or 200 millivolts, it's much less than the signal amplitude or the power value, power supply value of the voltage supply value. But this hundreds of millivolts voltage drop generally adds a noise, a direct noise to our design. So if you are designing anything requiring the lowest low noise low noise operation, this technique is definitely out of question. So be very careful here. Try to avoid this technique as much as possible. Use one of those. Those techniques are both good. So single source point and start point. What's the penalty though? Because you won't say, so why to use multi-point at all? So source point, a single point and star are so much better than I will always use it. In reality, it's not really so. Remember that we have in real applications, on real PCBs, we've got hundreds of so-called users. Hundreds, really, because each grounding is connected everywhere, and we have it connected to many components, which means that, of course, it is always better to use this technique or this technique, but it's not always feasible to build a PCB, PCB utilizing only those techniques. Usually, we have to make some sharing of techniques, and the optimal usually way is that the major ground tracks, the major ground connections are done against the single point or star point technique, but then locally we are using the multi-point technique. So usually we have a hybrid technique, and usually that's because of the limitations physical. It's not possible to use to make 200 separate connections. So physically, it's not viable to make 200 or 500 physical direct connections between the components and the grounding. Besides, another way we do it in practice is then we are sorting. So in order to avoid too many connections problem, we are usually also in a microcontroller, especially design, we are sorting the components, the elements of our design into four groups. The analog, digital, so all the elements about the low power analog, and low frequency, all the elements grouped close to each other, all the elements of the digital origin close to each other, grouped in a physical constrained space. All the elements of group number 3 for high-speed circuitry grouped with each other, and then all the elements of power supply and of high power as well, because in this pale red, whatever the color, or orange box, we are to place the power supply itself, but also close to power supply should be high current components here in this box. So 4 boxes, four areas where the components should be grouped, and this grouping allows or simplifies greatly. So it has 2 advantages. First of all, it's much easier to make a good grounding here, because then we can make a large, thick, low impedance connections from each of those groups together, and we can easily form the star or single source point the configuration, and then within the analog, within the area, then we can connect using multi-point. That's still fine. It will work it will work well, and it will guarantee good grounding. But another, so that's one advantage of this configuration of sorting the components physically on a PCB board into a few groups, into those 4 groups. Another advantage is are the radiated noises, especially the high frequency circuits. They tend to radiate the electromagnetic field in all the directions. And if they are, same is happening with digital circuits. Same is happening with digital circuits that because we have high frequency switching here, they also radiate the components, the tracks. They tend to radiate around themselves. So if we place for example, the high precision analog components close to high frequency circuits, then the EMI noises from the high frequency circuits will be then delivered through the air, through the electromagnetic waves to the analog components, and the good grounding technique would not prevent this because it will go wirelessly. That's a problem. That's also the second advantage of the sorting, that when we separate physically those noisy components between themselves or sensitive components, then we are avoiding also this kind of troubles. So remember, for good grounding, the usually hybrid technique is the optimal one, although we should try to make the star or single point as much as possible, but it's almost never possible to do it purely with this technique. Usually we are combining the star single point with multi-point technique, but we should combine it in a wise and clever way. So like you can see on the slide, the major connections to the major groups, and within the groups only the multi-point technique maybe use the major groups, analog, digital, high-speed circuits, and high current, because there is this group is a high current. So high current here, for example, motor control. So if you want to make to put a H-bridge current and to supply some relay switches for high. Usually they are about motors. Then it's there in this. And then it's in this box. What's interesting here? So here is an example about the connection. The best way would be to connect also VDD in this way, as also VDD with this hybrid star/multi-point technique. But frankly, the VDD, if you don't have such a capability, such possibility, so if your board is too dense to route a power supply the same way like a grounding, then the power supply can be routed in a multi-point technique. It's less critical. So the VDD or in general, the power supply routing is much less influences the quality of our design much less. The reason for this is that the chips usually they usually have the parameter of so-called power supply rejection ratio. So the circuits usually reject the power supply changes, reduce the power supply changes by many orders of magnitude, which means that any variations or any noises coming on the VDD line are less influential than the choices on the ground. The ground is critical. Remember, the ground has the highest priority with a PCB. The ground is sometimes omitted at the first. So the trap that the beginners especially fall quite often into is that you leave the VDD and ground for the end of the PCB routing, and first you start with component placement, then you do the routing of the signals, because there are many more signals. Many people think, and ground, what is a ground? But in fact, the ground really has a priority, and it's by far the most important signal out of all the signals on the PCB. So the planning of the ground is very critical. VDD, okay, you have to use thick. Normally, the only special thing between the VDD and the signals is the thickness of tracks. So because of this temperature rise, from practical point of view, the VDDs must be long, must be thin, thicker or wider. We talk about the width of the tracks. So the VDD tracks, the supply tracks should be wider than the signal tracks. So if you are using signal tracks like 10 mils, VDDs, you should start with 20 at least for VDD delivery, while the grounding should start from 30 mils. Of course, in special places you can reduce the width of the ground, but that should be those should be the starting point. So the signals, you should start with 10 mils ground, VCC with 20, and grounding 30 mils as a starting point. And again, depending on the density of your design, you can increase the thickness or width or reduce it, but the starting points, in my opinion, should be like this. Besides the good grounding, the power supply also is less critical, because we mentioned about the power supply delivery, and the power supply delivery is as well a bit less critical, because if we have a good ground, a good and low impedance ground, then we can also filter the power supply noises quite efficiently. So if the ground is bad, if the ground is noisy, then we can do really nothing. But if the ground, is good, then we can do quite a lot. We can try to filter out our signal, our power supply. How do we do this? Here we have two simple examples, two simple slides, two simple schematics with the power supply of some microcontroller, whatever the microcontroller is. And here we can see the basic rules. The basic rules of filtering our power supply lines. So first of all, we always start with a capacitor. Capacitors, which are usually 10 microfarads or more, as they should be quite close. They have to be present on the PCB. They should be fairly close to the supplied circuit. Their capacitance, as I mentioned, from 10 to 100 microfarads usually is the case. Then close to each input, we shall have the so-called decoupling capacitors. The decoupling capacitors are used as very low impedance sources for high frequency, especially operations. Therefore, in order to avoid the inductance we have here of the lines, the decoupling capacitors, as they are to deliver to filter out the high frequency noises, they shall be as close to the power supply pins of microcontroller, for example, as possible. But those decoupling capacitors are used as well for other integrated circuits, especially the integrated circuits that have digital switching inside, but also for even simple operating amplifiers. We shall use those decoupling to filter out, to clean out the power supply signal. Those decoupling capacitors, from practice, everybody. So the first shot is 100 nanofarads. So that's the first shot for the decoupling capacitors, but it's not unlikely. So if you get more skilled, you will see that sometimes 100 nano is not sufficient. Sometimes you have to add, for example, 1 nano, and additionally you have to add something like 10 picofarad. But that's not obligatory. Obligatory value is always 100 nano. So without thinking, each power supply pin should be is to be decoupled with 100 nanofarad. That's one thing. Second element that you can find here, that is visible here on the slide, is filtering the power supply signal. Here the filtering is on the example of delivering from one supply line, delivering a power supply to the digital part of the microcontroller and to the analog part of the microcontroller. The analog, as you know, requires a much cleaner power supply line. And the cleaning, because we have a good grounding, so the cleaning can be done most effective. So we can use RC filters. So the RC filter is this one. So the resistor and capacitor is doing the filter. So actually we have a pi filter because we have all this makes the filter, capacitor, resistor, capacitor. Yet we have today quite universal components, which are ferrite beds. We talked about it in the beginning. Ferrite beds, which are the inductors, special type of inductors, dumping, so with low DC resistance, but with quite a decent impedance at high frequencies, which does mean that the switching, or the high frequency noise that will be present here at this point will not be present at this point, so right after the ferrite bed, because the ferrite bed impedance together with those capacitances will filter out those noises. So this is one of the methods of reducing the power supply influence on the operation of integrated circuits and in general electronic circuitry. But still, remember, critical is the good ground. Without the good grounding, we are not able to do anything here. Then about the small remark about the straight capacitances. So those straight capacitances, so the capacitances coming from the planes, plane capacitance or track capacitance, and they may be useful, as we mentioned, for decoupling, but they may be harmful as well. An example when they might be harmful is, take a look here. So here is the reason, one of the reasons why we shall sort digital components from analog, or digital parts from analog parts, and place them in completely another physical place on a PCB board. Because we might have a situation where the digital track will overlap an analog one. And of course, the capacitance isn't large, because you remember it's about it's fraction of a picofarad per square centimeter, which doesn't seem to be much. Yet, if, for example, we make such a bar that we put a track on top, which is digital, and then track on bottom, which is analog, and if they overlap for a longer distance, then we will have situations where the signal, the noises from digital part, especially, that's especially critical. The signal will simply go through this capacitor to the analog part, and all the switching the switching that is visible on the digital line will then appear here at the analog pin, causing a lot of troubles, causing a lot of problems. So that's something. So this straight capacitance, of course, is quite nice if we have the ground planes and the signals then are decoupled to these ground planes. But these situations of overlapping the planes of digital world or high frequency board or high current switching world, they shouldn't overlap even through the PCB, because we may have such a problem. And for your because this lecture is not actually, we don't have enough time, and besides it's too early for you to go that deep, but just to give you some idea, the high frequency usually requires special design technique, and usually the avoid. So here we have an example of a very simple high frequency board with plenty of ground plane. So there, this is the ground plane, no vias on the path. So take a look, no vias here, just a plane. So connectors, input output, and some tracks with controlled impedance, size dimensions. And the power supply also delivered through lumped components, because this is the inductance. That's why the size is done in a certain way to keep to guarantee certain inductance for very high frequency. So generally, this is a special technique for high frequency. During BSc course, engineering course, I don't think there is any subject about it. It's definitely during MSc courses later you get your education. So far, that's enough. Important thing that also has to be at some point considered is the clearance. What is a clearance actually? Clearance is the distance between tracks actually. So if we get back to our first slide today, there was this parameter TT. So track to track distance. That's the clearance. The clearance is the clearance between tracks, or between tracks and paths, or between paths. Of course, at one side it is limited by the technology that we possess, technology that is available from the manufacturer. And then you remember it was 0.25, 0.2 millimeter, even 0.15. But the problem is also that the clearance is limited on the other side by the voltages that are, or the potential of the tracks. So there are certain norms that I want to really go very deep into. But for example, for 220 volt AC main power supply, the spacing between tracks should be about 8 millimeters. It's an absolute minimum between tracks if the tracks are not insulated. So if there is no protective layer, and then this 8 millimeters is really minimum. Quite often on the PCB, we are making a special space between with some drill or on some milling machine. There is a break in the PCB between such traces in order to, even if this is 8 millimeter, because this poses a serious problem. So if there is a track, one and second one, then quite often a copper. So even if there is an 8 millimeter here between the tracks, quite often we are adding some empty space. So we are breaking actually the PCB, so that the current may not flow there, and there will be no short circuit between the tracks. That's the problem. There are special norms for it. There are special norms for it with the for non-DC. So for non-main, so for DC, the norms are a bit softer. So from 0 to 15 volts, on the internal layer, there should be clearances of 50 micrometers at least. For internal layers, and 100 microns. Take a look for the external, 100 microns So that's why 3.5 mils and lower, only for very low voltages. From 0 to 15 is usually usual case, because usually the electronics we are designing somewhere here, but still we can't get below 0.1. That's in the norm. For internal relays is better because they are insulated external. There is an access to the air and the humidity as well. That's why the limitation is higher. For the higher the voltage we play with, of course, the worse it is, and the higher the clearance is. But again, this is not for AC main. Those limitations are only for DC. Good. Then the construction of electronic devices with the fabrication. So the routing is finished. So now the fabrication. The case of fabrication, we are starting. So when the PCB is ready, then we are the software we have is automatically generating. So sometimes we have to push it, but in general, it's generating so-called manufacturing file. So manufacturing files is a set of not Gerber, but it's a set of vector files, usually text files in general. Those text files, there are a couple of those files. They are delivering an information for the manufacturing of the PCB, and then for the assembling of the PCB with automatic tools. And so the manufacturing files are telling us not only about the layers, but also about the holes. That's quite natural because our PCB have vias, have various connectors, and the placement of the positions of the holes and the sizes of the holes must be given as well. So they are all available within this manufacturing files. For manufacturing of the PCB, we have Gerber files and the Exelon drill files. These are the files that are usually used. So it's not about PDF, so we can print a PDF. So when you design a PCB board, you can print a PDF, for example, or make a print screen and make a bitmap file. But of course, it has no use for professionals. For professionals, we always generate when you want to deliver your project to a company, we generate Gerber files or together with the Exelon drill files, because they are together. What are the Gerber files? They actually, each layer is described in the Gerber files. How many layers we have, even the mechanical layers are generated. There is generated a Gerber a vector file with this layer. In general, they instruct the equipment where to go and what to do, and what to do with what instrument, because that's for plotter, because that's what the Gerber file is. So they are known in this is so-called standard photo plotting language, known under the name of RS274D in the industry, developed in 1980s, but modified, but still widely used. In general, it's just the ASCII file. It's just the plain text file instructing the plotter to move to use a certain tool and to move from one place to the other. So these are a purely graphic file, therefore keeping the size, because that's what it is, keeping the dimensions of all the tracks and all the pads and planes and so on. The Gerber files. So in case of Altium Designer, the Gerber files are And so there are Gerber files for each of the layer as mentioned. So we have a separate Gerber file for top layer, separate for bottom layer, separate for medium layer, separate file there is for top overlay, bottom overlay, mask layer, solder mask layer, also for mechanical layers and for keep out. And then when we deliver everything, when we want to send a project for manufacturing, we have to prepare those files. We have to generate those files and then wrap them together, zip them together or whatever, and send them to the company. The good thing about the Gerber files is that first of all it's a standard, and second of all is that they are very space efficient. So it turns out that then those, even though this is not a binary file, even though these are the text files, but because they are graphic and because they are in this files, they are just coordinates and the tools used, and thus those files are the project which takes on during the design phase megabytes on hard disk drive. After generating Gerber files usually go into kilobytes, and after zipping or RARing, it's single kilobytes quite often, because the ASCII files are compressing very well. Okay, and then when we have these files, then we can try to make our own PCB. But actually, we have just 1 minute left, so the major points behind, so the major techniques of making your own PCB at home, and what's the difference between making the PCB at home and making the PCB in a company, was the technology behind those two production techniques, and more on this next week. So thank you for today. As a reminder, next week the lecture will be a bit shorter because we are starting at 12:15. So instead of 11:15, if you have any questions, don't hesitate to send me an email or write or try to contact me physically or on Zoom. Anyway, thank you very much for today, and have a nice day. See you next time. Bye-bye.
Thank you. Goodbye.
Bye.